my viewers, feel most welcome into our today's discussion, whereby we are going to discuss about the inverse Laplace transform. When you've been given a function like this one, to find the inverse Laplace transform of this function, the first thing that we need to check is on the denominator. And when you check on this denominator, it is a linear second order equation. We are going to use the complete square method in working out our denominator here. So on our denominator, and by simplifying this denominator, we are going to have s squared. We add to 4s, we subtract from 5 is equals to a 0. To mean that s squared, we add to 4s is going to be equals to a positive of 5. What do we understand by the complete square method? We must introduce the term of c. When it comes to the term of c, c is going to be equals to b all over 2, everything squared. To mean that our c will be equals to, our term of b was equals to 4 all over 2. And here we come and square everything from the formula to mean that our c will be equals to 2 squared. We are going to introduce our term of c on our left hand side and on the right hand side, whereby now we are going to have s squared, we add to 4s, we add to 2, everything squared is going to be, equals to 5. We add to 2 squared. Here, on our left hand side, we are going to collect the common term of squared. S, we come and add to 2, will form a common term of squared. And on this side, we are going to have 2 squared, which is equals to 4. When we add to 5, we are going to have a positive of 9. To mean that we can rewrite now the whole thing and say that s, when we add to 2, s, when we add to 2 squared, now here we are going to have a negative of 9. And this is how you go about simplification of whatever we are having here on the denominator. Let us now rewrite everything. We are going to have the inverse Laplace transform of 2s, we add to 5 all over s, we add to 2, everything squared we subtract from 9. When we check here on the denominator, it means that shifting has been done somewhere. Let us now relate whatever we are having here on the denominator and our function on the numerator. If you want to relate these two, that one means that the term of s here must be shifted, and we are going to introduce a known to this term here to mean that we are going to have s, we add to 2, whatever we are having here on the denominator, we come and add to our term of a is going to be equals to 2s, we add to 5. We are relating whatever we are having on the denominator with whatever we are having on the numerator due to the shifting that is here. And when you check here, 2, the term of s has got a coefficient of 2, to mean that we come and introduce that 2 here. When it is having 3 here, at this point, just come and introduce that 3 at this point. But here we are having 2. Now, we are going to open the bracket and get the value of a, because a is the unknown that we need. And here now we are going to have 2s. We add to 2, we add to 4. We add to a is equals to 2s, we add to 5. Here 2 is a positive. When we take it to this side, they are going to cancel out, and we are going to have 4 plus a is equals to 5. A will be equals to 1. Now, we are having the value of a, and we can rewrite now the numerator to be, the inverse Laplace transform of 2 into s, we add to 2, we come and add to a, whereby now our a is a positive of 1, all over s, we add to 2 squared, we come and subtract 9. Up to this point, we've only rewrite the numerator with respect to our shifting. That is the reason as to why we must work this part. Now, when you check whatever we are having here on our numerator, if you work it out, you must get whatever we are having here. Let us check. When you multiply this one by this, we are going to have 2s, we add to 4, we add to 1. And when you simplify whatever we are having here, you must end up to that point. That one means that whatever we are having on the numerator is right. Let us now rewrite the whole thing from here. From this point now, we are going to have the inverse Laplace transform of 2 s, we add to 2, all over s, we add to 2, everything squared, we come and subtract from 9, we come and add to 1, all over s, we add to 2, everything squared, we subtract from 9. From this point now, we must get now into the first shift theorem. When it comes to the first shift theorem, we agree that the Laplace transform of exponential positive or negative of a t cos our angle with respect to t is equals to, we say that we first get the Laplace transform of cos our angle t, and cos we understand s all over s squared, we add to our angle squared. Since it is a first shift theorem, it means that the term of s will be shifted, and here we are going to have a negative or a positive of a, the term of s being shifted, and on the denominator now we are going to have s, negative or positive of a, everything squared. Let us now come and check at this point. You will find that when it is a trigonometric function, we are having a positive sign here, to mean that we are not going to use the trigonometric function. Let us check on the hyperbolic function. When it is an hyperbolic function, the Laplace transform of exponential positive or negative at cos hyperbolic, our angle t is going to be equals to, we are going to have s all over s squared we subtract from our angle squared. This is the Laplace transform of cos. But here we are using the first shift theorem to mean that the value of a must be, the value of s must be shifted. And now we are going to have a negative or a positive of a. We only shift the term of s, and here when we shift our s, we are going to have s negative or a positive of a. But since the term of s was squared, we come and retain our square. When you check at this form, it resembles this function to mean that we must have our answer as exponential at, either positive or a negative, with hyperbolic function. That is either a sine or a cos. Let us now start our working by now getting the inverse Laplace transform of this function. Here, for the cos, you will find that for the cos it is going to match this function. But when you check this one, it a kind of resembles for the sine. Let us now get the Laplace inverse using the first shift theorem at sine hyperbolic our angle t. Here we are going to have our angle all over s squared, we come and add to our angle squared. Since the term of s is being shifted, it is only this term that will be shifted, and now here we are going to have s negative or a positive of a everything squared. Let us now start working with our first value here. We are going to have the inverse Laplace transform of s we add to 2 all over s we add to 2 everything squared. We come and subtract from here, we are going to have 3 squared because 3 squared is equals to 9. We add to the inverse Laplace transform of 1 all over s we add to 2 everything squared we subtract from 3 squared. When you check at this function here, the inverse of our first function here, it resembles the one for the cos. And now we are going to have exponential. We are going to have 2 exponential. We say that when we are having a negative of a, here we are going to take a positive of a. Let us now come into this function. It was shifted with respect to a positive of a to mean that here we are going to have a negative of 2t. Cos hyperbolic of our angle here. Here we are having a negative to mean that it must take the hyperbolic function, and now we are going to have the cos hyperbolic 3t. We come and add to, this is now the inverse Laplace transform of our function here. The inverse Laplace transform of our function here is equals to whatever we are having at this point. Let us now check on this function here. For us to do this function, we know that it resembles, here we are supposed to be having a negative. we know that it resembles this function. But when you check here, we are having 1. To mean that for us to have 1 here, we must multiply this function by its reciprocal on both sides. And when we multiply this function by its reciprocal, it is going to cancel out. And now we can come and have 1 all over our angle exponential positive or negative 80 sine hyperbolic. Our angle t is going to be equals to 1 all over s positive negative all positive of a, everything squared, we come and subtract from our angle. Now, here we are going to have 1 all over our angle lambda here. Our angle here is equals to 3 exponential. It was shifted with respect to a positive of 2 to mean that when we are having here a positive, here we are having a negative. Here it is a positive, the exponential part must take a negative of a. And here we are going to have a negative of 2t. Negative stand for the sine hyperbolic. Our angle here is equals to 3t. And this is how you go about finding the inverse Laplace transform of this kind of equation.